在上课了。So last week, we talked about dating. Then for next week, so under the Lorentz, we explicitly say the two physical degree freedom for photons. We also talk about how to couple in the matter. So last we write down, we didn't really divide, we write down before. So we discussed a few different gates. We'll continue to see the consequence of gate marks maybe after a few weeks in the level of the amplitude. So basically, after here, we finished all the discussions about spin 0, spin 1 particles. Okay. So the next we're going to spin half. Because as you know, in our real world, electron is spin half. So we have to study this spin half particles. So here's the main for spinors. So what is spinors? That's the first question. How to define spinors? So do you know how to define spinors? Spinor is a language to describe the spin half particles. As you may imagine, following the same logic we discussed for spin 0 and spin 1, we have to find some representations, right? We have to find some representations. There are a few different levels of these representations, okay? The easiest level is we have to find something like a Lorentz vector, or, yeah, so you can transform it under Lorentz transformation, for example. And the second level is we have to find the physical state, right? That's a more deep level, okay? Then the physical state that they can transform under the unitary representation under Lorentz group or Poincare group, right? These are different levels, okay? In the first level, we didn't require uniformity, really, because as you can immediately check, those transformations are not unitary, okay? They are not unitary. Because of that, we didn't require unitarity, you can find it more easily, okay? But if you want to seek for some unitary or physical representation, you want to find the representation given by the physical state, meaning the quantize that Spin-House particle state, then you have to do more work, okay? You have to quantize the field. But let's go step by step, okay? So the first step is to find something like Lorentz tensor or Lorentz vector, okay? But this time for the spinors. So for that purpose, as you can see, everything should be determined by the representation, right? Everything should be determined by the representation. So spinors must belong to a particular representation, okay? That's following the logic you can imagine, okay? Even though we at this moment we didn't find it yet, you can imagine. Yeah. So we will go through these steps. So here, what do we mean by representations, right? That's sometimes also can cause a little confusion. So we have to start from. So in that sense, we have to start from. We have to start with talk about representations of the Lorentz group. So if we talk about the representations of Lorentz group, again, there are different aspects. Okay? For sure, if you give me a Lorentz transformation in an explicit form, for example, 4x4 matrix, right? So, of course, this is the representation, right? You can check it, metric, because this transformation you can take product, okay? Product means matrix product. Then this 4x4 matrix give you a representation. But sometimes for physical purposes, we also call the vector space. This 4x4 matrix act on, okay? It's also a representation, okay? The following group theory, you can justify yourself. This is also a good representation. Meaning what? Meaning a transformation just send some vector to another one, okay? So because of this property, this vector also represents the group, okay? Right? So both are correct. Both are correct. Okay? So sometimes we just sometimes we use this representation to refer to different object. That's the first point that we have to clarify. Okay? So then let's start from the easiest one. Meaning that this is really go back to the lecture 1. So let's go back to lecture 1 to remind ourselves there are a few Lorentz transformation matrix. As you remember, because this Lorentz group here is really useful to reduction plus and boost. Okay? Plus and boost. Actually, there are 6. There are 6 independent ones. Okay? Do you remember? There are 6. Each one has a finite parameter. Okay? The finite parameter parameterizes how you rotate and how you boost. Okay? So these are the they are all given by this 4x4 matrix, and then 4x4 matrix. For example, there are 3 rotations. It's given by this 1, 2, 3. Remember, 1, 1, cosine theta, tan theta, minus sin theta. Cosine. Yeah. We label this x, because there are 2 more rotations or rotate around the y-axis and the z-axis. Okay, I'm just going to skip it. Okay, you can go back to lecture 1. These are the 4x4 Lorentz transform matrix, 4x4 matrix. What's the boost? For example, something like this, cosh, right? Remember, this is the cosh, right? The cosh function. So this is the cosh beta sandwich. Also, 4x4 matrix. I also label this as x, and there are 2 more depending on 4x4 matrix. Right. And the x means you boost along the x-axis. Boost along the x direction. So why we again just write down this 6 matrix we already know in the very beginning? Because everything, because we have to start from here to find this particular representation. Support spinors, okay? Because logically, spinors should stay in some space, okay? In some space. That space represents Lorentz group or Lorentz transformations. But there are many different representations, right? The spinor belongs to one particular, okay? So we have to start from here. But essentially, because there are different representations for the represent the Lorentz group. For example, this is the so-called matrix representation or 4x4 matrix representation of the Lorentz group, and this representation, this also belongs to a particular representation. Okay, if you want, right? Even though you shouldn't think that this 4x4 matrix is a definition of Lorentz group. It's not true. It's just one representation. Is that clear? Why? Because clearly this kind of thing can only act on the 4 vector, right? It belongs to the representation associated with the 4 vectors. Okay. So these representations act on the 4 Lorentz vectors. Okay. But there should be many others. Then the immediate question is, since there are different representations, since there are many different representations of Lorentz group, the question becomes how to characterize Lorentz group in some way which does not depend on the representation, right? You don't want to do case by case, right? You want to extract some intrinsic property of this group, okay? You don't want to do every time write a particular matrix and then understand it. That's a little weird, right? Then how to extract? How to extract intrinsic? This is the question. I guess maybe there's homework related to this stuff. So in math terminology, this is called we have to go from group level to algebra. Okay. Because this is a continuous group. So if you go from group to the algebra, or Lie group, from Lie group to Lie algebra, it means you have to think about what? Yeah, computers, but where does the computer come from? Okay. Yeah, well, think about infinitesimal transformations, okay? Infinitesimal transformations, okay? Because this is a continuous group. If you know the infinitesimal transformations, meaning you know the some local structure near the identity, okay? Near the trivial transformation, then you can generate, okay, all other finite transformations. This is the nature of the Lie group, okay? So we have to go from Lie group to the algebra. So in order to find this algebra, we have to do the infinitesimal transformation, okay? But of course, start from the finite transformation is pretty much easy to find the infinitesimal transformation, right? What do? The easiest way is just do the small parameter expansion, right? You just do the small parameter expansion. Just think about all these parameters, not finite but small, okay? Then you expand it, right? You do tensor expansion. Then you keep the leading order. That's it. Then you find, of course, this because this is only a leading order. You'll find a much simpler matrix, okay? Compare with those 6 matrices, okay? Then you find those a very simple matrix. Then you think about the commutators. As said, then you find the intrinsic structure of this Lie algebra, okay? This is very easy. I mean, sometimes you may be scared by Lie group or Lie algebra. Forget about this names. It's very simple terminology. Okay. Very simple terminology. So let's do it. So let's do it. For example, we can do the following. These are the 6, right? As said. So the most general Lorentz transformation can include all these 6 parameters. Is that clear? Which means you have to think about the product of this, that, those 6 all together. Okay. Then your 4x, again, you get 4x4 matrix, right? From your linear algebra. Okay. Then you have 6 parameters, independent parameters. Okay. This is the most general Lorentz transformation, which is send a 4 vector to another one. Okay. Then you can do the small parameter expansion together, okay? Okay, to save your time. You don't need to do one by one, just do them together. You take product and do the 6 small parameter expansion. Do small parameter expansion for 6 one, okay? Then you will get a simplified form of the Lorentz transformation, so-called infinitesimal Lorentz transformation. Okay. So let me write this for you. In this case, for the above 4 vector. For this 4 vector representation, the infinitesimal Lorentz transformation becomes as follows. Okay, I'll just use delta. Okay, we're familiar with this language because we talked about infinitesimal transformation before. When we proved the Holder's theorem. Okay, we can write in this way. Example, this is in a component form. Okay. Because we want to write it more explicitly, so you will get something like this. Right. So this is the infinitesimal transformation. This is the infinitesimal transformation. This is a simple exercise, right? You can do in 1 minute. Okay, do in 1 minute. You'll get this one. Okay, you'll get this one. This is in a component. Well, what do I mean? But this delta should be defined as the x naught prime minus x naught, right? Prime means after transformation. Okay. This is before transformation. So this defines the delta. Okay. The point is, this can be expressed in terms of x itself, okay, with some linear coefficient. And actually, this is I run from 1 to 3, and beta tutor and theta tutor is nothing but the corresponding small parameter corresponding to this theta. Theta is the rotation angle, and beta is the boost parameter. Okay, you can check yourself immediately. Is it true? And right, and these are the 6, right? The number of the parameters shouldn't change. Okay, because becomes a little small parameter in infinitesimal angle. And the epsilon, this is a total symmetric, total anti-symmetric. A symbol with epsilon 1, 2, 3 equals 1. Okay. And totally symmetric means start from here. Whenever you flip, whenever you exchange two indexes, the sign flips. Okay, the sign flips. Then you determine all the epsilon elements. So this is called epsilon. I might think that this is in terms of element. This is infinitesimal transformation. It's not that elegant. That's true, and we can reorganize it a bit. So this is actually can be written in a more compact form, which is in terms of vector. Delta x mu equals to I sum equals 1 to 3 theta I theta j I mu plus beta tutor k I mu. And this one maximum mu. Okay, I just rewrite it. Okay, in a more elegant way, or in a matrix.
The I here is the imaginary number or the 它这个 I 是虚数单位还是
This is I, of course, is the imaginary. This is another question. Yeah, this I is that index, but this is of course not. So I just package it in this form, right? Of course, you can do that because yeah, this is almost definition. Why I choose to do it in this way? The real purpose I want to do is really I want to extract this so-called J and K matrix, right? Right? You see? So in this way, apart from the small parameter, which is a number, okay, there's some 4x4 matrix structure appears. See, these are the 4x4 matrix. Okay, let's have a few funny index, but you can easily understand. This I means there are different J matrix, right? And for each J is the 4x4 matrix. Okay. But they have a new index. So if you think this is a 4 vector, all these J and K are 4x4 matrix. But there are 3J and 3K, okay? That's what this index notation means, okay? But it's fine, right? It's not a big deal. that in this way, we can find this particular J matrix, for example, J1. I'm just specifying with I run over from 1 to 3. So let me write all this J and all this K. So J1 will be this 0, 0, 0, 1, 1, plus 1, 0. And J2 will be 5, 0, 0, 0, minus 1, plus 1. Okay? And J3. Times 2, 1, 1. What's the way to do this? Okay. And you can observe what is the relation between this J matrix and the Lorentz transformation for finite parameters there. Okay? There is a simple relation. You can okay, so what is the relation? We need to check. Because this matrix represents the infinitesimal transformations, okay? And this matrix are the finite transformations, right? So you can imagine that I can manipulate this matrix, okay? To do what? Find those J and K. For example, let's do this one. This is the rotation with the parameter theta. So in order to get the infinitesimal matrix written there, I can use this matrix. First, expand the theta, okay? First, expand the theta. So what do you do? Tanner expansion cosine theta? Leading order? 1? That's correct. It's 1, right? It's 1, right? You only keep the leading order. So this is 1. This is the 1. What is this? Theta, right? This is minus theta, right? See? Now use this matrix after the small parameter expansion. Then subtract the identity, okay? Because this is infinitesimal delta. So you minus the identity here, okay? Minus the identity. So this becomes 0, 0, 0, 0, okay? And then you extract out the parameter in front, okay? So what do you left here? Minus 1 and 1, okay? So which matrix is this one, right? So you get this one. So you have a 1-to-1 correspondence between those matrices and this matrix, okay? But now the claim here is these matrices can capture the intrinsic property of this Lorentz group. In other words, we don't quite need those full matrices, right? We only need this infinitesimal matrix. That's the point. Okay? The point is those finite matrices can be generated using some some unified formula. Okay. Right. Just after you know this kind of matrix, you can get that easily. Okay. Okay. Not the inverse way. Okay. So what do we do next? So someone mentioned we have to consider the commutators. But before that, let me make it more clear. These matrices are called the generators. generators of Lorentz in the four vector space, okay, or in the four vector space. So why we call this generators, right? Generators seems very important, right? Something you can take use to generate others, okay? Which are called generators. 生成员 generators. They generate the group in the sense any finite transformation, let's say lambda. Remember that we use lambda to describe the finite Lorentz transformation, right? So any finite transformation can be written in this form. Okay? So this is the claim. Okay, so this is an important equation because it's very, very universal. Okay, it works for any unique group. Okay. If you know these generators, then you can put them together with these parameters, okay, and do the exponential, okay, do the exponential, okay. Then someone will ask, I don't know how to compute the exponential with an operator. Well, yeah, that's a good question. You can check yourself. There is a standard mass formula, okay, to deal with such kind of exponential with the component, the matrix or operator, right? There's a standard mathematical formula tells you to do. Not a big deal, okay? You just follow the formula, mathematical definition. It gives you the result. Okay. But as physicists, we should understand that this is in a very clear manner, right? Because this formula we see many times. When we deal with this another theorem, we also mentioned the conserved charge is also a generator. Remember that? Okay. Whenever there is a conserved charge, you can also plug into this position of J or K. Okay? Then you get an exponential I alpha Q. Okay? Where Q is conserved charge, and then you get the unitary operator. Okay. That unitary operator is essentially this one. Okay. This is in a more universal language, this is called the unitary operator, okay? It implemented the same transformation, okay? Here is the same thing. That's why it just does the particular job for Lorentz transformation. Right? But the important thing is this works even for all the global symmetries, okay? All the global symmetries continuously. So this formula is very universal, okay? And alternatively, this J or K, you can call it generators. Okay, generators. Another remark is, you might think, okay, if you ask me what is J and K, I just think this is the definition. That's not true. Okay. Okay. For generators, there is also a way to represent it, right? But this J and K, they are very intrinsic generators. You can represent them in different form. This is only one way. Okay. This J and K turn into this form as a 4x4 matrix, but it's not unique. Okay, can you see that? Right? Why? Because here, in terms of 4x4 matrix, essentially because we are in 4-vector space. You put your Lorentz transformation in the 4-vector space. Okay, you transform this 4-vector to another one, then you get because of that 4x4 matrix. But if I turn to another representation, this same generator should be expressed in another form, okay? Is that clear? So this is not unique. Don't think this is the unique way to represent the generators. Generator is generator, okay? It's a very intrinsic object. You can represent it in different, but the same generator. That's another comment, right? So as someone mentioned already, with this one, what can we do? So with these generators, to understand the relations, we should consider, we can find the following relations, okay? What can we do with these generators? We can do the following. You can check the commutators, right? Because these are matrices, you can easily compute them. You can check it, Ji, Jj equal to I, epsilon, Jk, Jk. You can easily check the commutators, right? With the matrix, if you compute this one, you're getting it. Okay. You check this out. Sound familiar relation? What is this relation? Have you seen this in your quantum mechanics? Right? What is this? What is this commutation relation? That's right. This is the commutation relation for angular momentum. Okay. Precisely the same one. Precisely the same. Okay. Including all the coefficients. This is the relation for the angular momentum. We'll explain why. There is a bunch others. For example, you'll get a J, if you commute J and K, you'll get an I epsilon K. Okay? Then the remaining one will be what if I commute Ki and Kj, then you'll get a minus I epsilon Jk. Okay? That's it. You see, I only have 3J and 3K. So this should be the full commutation relation. Okay. So I consider all the J, Jk, and Kk. Okay. Then this is the result. That you already observed that this is the familiar angular momentum commutation relation. Why? Because the generators for the three-dimensional rotation, remember that here J, I start from there and then extract this J. But this J are all the matrices associated with 3D rotation, right? See, because these are the three rotation matrix, just the rotation. So essentially, because the angular momentum is nothing but the generators, okay, of the 3D rotation. So it's not surprising. Here, I use the language of generators. I get this precisely the same commutation relation with the angular momentum. Because angular momentum is the conserved charge associated with 3D rotation. Okay, the same thing. You can say the generator is the conserved charge with angular momentum. The same thing. Okay, for 3D rotation. Okay, but of course, Lorentz transformation is more than that, right? So this 3D rotation is only a subgroup, right? It's only a subgroup of the Lorentz group. Okay, so as said, this is some relation in the level of the algebra. Okay. Then there should be also a sub-algebra, right? So this relation essentially defines the sub-algebra of the entire Lorentz algebra. Okay. So what I mean by that, you can see these three relations. So what I mean by this algebra, sometimes it's scared. So it's not a big deal. You can view and think of these three relations defines the algebra. Okay. The so-called SO 1,3 algebra. Or Lorentz algebra. Right? And this is a sub-one. Okay. And this JJJ, only the JJJ is a sub-one. As you can see, why is the sub-one? Because this commutation relation does not touch others. For example, K, right? Right? It gives a closely algebraic relation among only the J, okay? Right? But for the other two, you have to touch K, right? Right? J and K are mixed, okay? You have to touch K. JK equals to K and KK equals to J, see? So this is a sub-one. This is the absolute truth. Okay? This is the reason why this seems familiar. It's the same thing. The same thing. It's the same thing as what you learned in your quantum mechanics. And yeah, there's another name for this bracket. Okay. So this bracket in quantum mechanics over here, we can think it simply as the commutation relation or commutator. Okay. We define this relation by the JI minus JJ. Okay. But more formally, in the a chapter of Lie algebra, this bracket sometimes also called the Lie bracket. Okay. Okay, just a short remark. Sometimes we call it Lie bracket because a mathematician want to make this very formal. Okay. To mathematicians, all the explicit expressions are some realization. Okay. The nature of all those explicit forms should be very, very abstract. They want to make everything abstract. Okay. So there's also a name, called this bracket as Lie. Meaning that they don't want to think of this bracket always in terms of commutators, okay? We just want to think of this bracket as a formal relation, okay? And give their name, which is called the Lie bracket, okay? Okay? But okay. We don't want to do that. We don't want to do that. So as already observed, there is a subsector of these relations, so-called SO3. SO3, yeah. So another comment about the notation. So sometimes if I want to specify the notation as a group, I will write a group as O, okay? If I want to emphasize this is only an algebra, then I will write a small s, okay? I write a small as well, also here. The small means the algebra, the bigger one is the group, okay? So this is the 3D rotation. This is the 3D rotation. Now, as I said, why should we view this relation are more fundamental than this explicit form of this J and K, okay? This is only one particular realization of this J and K, okay, in terms of 4x4 matrix, as I said. And the more fundamental thing is are these relations. Okay? These are relations that are very important, extremely important, that I want to point out. Okay. So we go step up from the finite transformation up to here. Now, you should think the logic in a reverse way. You should think that these relations are more fundamental, okay, than any others, okay, any others. These are the fundamental relations. These are the fundamental relations. And sometimes people also make these generators in a more fancy expression. Looks like so one can organize all this JK in a more compact way. You can already put them together to form another 4x4 matrix. This is 0, K1, K2, K3, and minus 1, 0, 0, 0, and minus K2. Means K3, and minus K2, minus K1, and 1, and minus 2. Okay? Because we have 6, okay? We can use these 6 objects to fill into a 4x4 anti-symmetric matrix, right? Because a 4x4 anti-symmetric matrix has only 6 elements, okay? You see from here, it's anti-symmetric. This is 0, or this a pair, okay? Then only 6. So we can put this J, all this J1, J2, J3, K1, K2, K3 into a more compact form. But it's not a big deal, it's just expression, okay? Make you to easily remember, maybe. Okay? So you can easily remember this matrix. So in terms of this matrix, this commutation relation becomes a little simple. Okay? It's a little simple. For example, you can try to not that simple, but it's really difficult. So it's a more compact form. But the whole point is the definition of this, the definition of this way with this relation is completely equivalent to this commutation relation. It's just another expression. Okay, it's not a big deal. It's rewrite in another form. Okay, and you can even write the finite transformation in terms of the Weyl, which you call the lambda Weyl, equal to exponential I theta Q V union. Okay, and theta is V in this way. Okay, V is this. Theta is the parameter. But this sum is trivial. It's not some fraction or whatever. This sum is trivial. It just says for each element of this way, okay, for each element of this way, there is associated parameter, which is the numbers, okay, in front, okay. Then you sum over all the together, okay. So do you have any question about the commutation relation of the Lorentz generators? So after this, a little bit exercise, then we can now talk about the big aim, which is to classify the representations. Okay, we want to classify the representations, right? The logic is we start from one particular representation, which is the 4-vector space representation. We go blah 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 to extract the fundamental relations, right? Now we ask the different question. If we think that this is the fundamental relation, to define this algebra, control this Lorentz group, then can we go from there to classify all the possible representations? Okay. Right? Why? Because then some representation will touch this particular representation prepared for Spinors. Okay. Eventually, we will find which one incorporated Spinors. Okay, that's the logic. So how to classify? The irreducible representations of the Lorentz group. Okay. as you can see, in contrast to Wegener's job, okay? Wegener's work, we didn't really require unitarity here, okay? We only say irreducible representations, right? If you demand the unitarity, all these are garbage, okay? You can check it, they're not unitary, you see? You can easily check this boost transformation are not unitary, okay? Then where is my, maybe I use it. Yeah. They're not unitary, okay? So it didn't require unitarity. If it requires unitarity, much more work has to be done, okay? So this is the more simple problem. So to do this, let's use a little bit of trick. So let's try to rewrite, again rewrite, we rewrite many things, you see? We did nothing but just rewrite. We rewrite it, now we rewrite these three relations further, okay, into another form. So this time we define this on J plus, okay? We define this on J plus. J plus is the half. J plus is the half Ji plus I, K, I. And we also define the J minus I. It's defined as a half Ji minus I times J, K. Okay? And then you can easily check that three relations can be expressed in another form. Okay? Then it becomes Ji plus J plus mu, and you get I epsilon ijk J K plus, and you get J minus, okay, J minus commute equals to I epsilon ijk J minus K. And also J plus and J minus don't touch or commute, okay? It's there. So why we do this? This is always a trick we do usually, right? This is called that we separate, you see? Now we separate this algebraic relation. We separate this one, right? We separate it into two sectors. Let's say in terms of plus and minus, and these two sectors don't touch, right? Don't touch. For these three relations, there is one piece somehow separated from other, but these two, they don't really separate it completely, okay? Okay? But in this way, we separate it completely, see? That meaning all these plus and minus, they don't touch, okay? They commute to zero, okay? Only themselves survive. Let's say plus, you get plus, minus, you get minus. Okay? But the point is, still, this relation is the same relation, you see, right? Is that clear? You see, this relation is the same relation with this one, okay? Okay? So, in that sense, since as said, the relation defines the algebra itself, okay? The relation defines this algebra itself. It's perfectly okay. You think about, you start from here, okay? Because these are just equivalent relations. You just start from here. You see these relations, you say, okay, since I got these relations, I can call this relation define the algebra of the SU2, okay? Or SU3, the same thing. In algebra level, they're the same, okay? Or 3D relation, rotation algebra relations, okay? All that's the same. So in this sense, we can see this SO 1, 3, which is the Lorentz algebra, will be decomposed into two SU2. Here, let me use SU2 instead of SO3. They're the same algebra. Okay? Because of this relation, I can claim this equation. Okay? This entire this entire algebra relations will decompose into each one each plus will give the SU2, another minus will give SU2. Okay? Not a big deal. And don't forget your original in corpus space, your original 3D rotation generator is not this J plus or J minus, it's combined one. Okay. Because this is another expression. Okay. J plus and J minus divided from the original one. So inversely, the original one can be expressed in terms of J plus and J minus. So the relation is, if you know the J plus and J minus, you should add up them to reproduce the original J. Why we emphasize original J? Because the original J really does the physical rotation in the original mean corpus space. Okay. Okay. This is just the alternative algebraic form. Okay. And the original K is the I J minus J plus. Okay. Okay. So someone may ask, what do you mean by plus? Okay, this plus. This plus, the meaning of this plus is very simple. In the algebraic level, this plus just means you put the generators together. Okay. For some of the generators, you clarify all the possible relations, right? But what if you put more? Okay. Okay. Then I put this plus and minus generators together. Okay. Then I find this commutation relation. I realize that their commutation relations don't touch each other at all. Therefore, I can define this plus. Okay. This is the meaning of this plus. Okay. Actually, in the group level, this is not plus, but instead it's some product, mini product. Because this is the algebraic level. What are the generators? So you just put them together. In the group level, meaning what? If you want to manipulate the group element, meaning what? When you take product, right? When you take product. So this relation in the level of the group is promoted to a product. But at this moment, it's just a sum. We define the sum by putting these generators together and clarify all the commutation relations. That's the definition of this plus. So why I want to do this, all this looks very simple but worrying exercise. Okay. Now it comes to the core. Why we want to do all this stuff. The core is here. We want to classify all the representations of this one. Okay. This is our original problem. Now I decompose this problem into two pieces of the SU2. But the point is now for SU2 representations, this is a much easier problem. Okay, we even know the answer from quantum mechanics. Okay, in quantum mechanics, we already know how to represent the SU2 in a very elegant way. Okay, now all this process now decompose the problem to represent a Lorentz group into two problems. Okay, to represent the SU2. Okay, but these two problems are the same, so I'll just decompose it. Okay. So up to now, we know we almost get the answer, right? Almost get the answer. Why? Because we know how to represent the SU2. Now, since SO1 comma 3 is 2 SU2, we know how to represent this SO1 comma 3. Right? So how to represent SU2? For this, we have to go back to quantum mechanics. So in quantum mechanics, we know what? We know the problem to represent SU2. What is that? Hmm? Yeah. So first of all, these are the very abstract form. Okay. Let me make it more concretely. Let me make it into a concrete way. And in quantum mechanics, we know the algebra. We know the algebra of SU2 is the algebra, nothing but the algebra of what? Pauli matrix, right? Do you still remember the Pauli matrix? I write it for you. You can easily check. The Pauli matrix relations are precisely the same computational relations. Yeah, right. Okay. We do know very familiar algebra in terms of Pauli matrix, nothing but these JJ relations. So Pauli matrix is this one. Okay, you can check it. Okay. You easily check system relation with set. And we also know this is first. Second, we also know that each irreducible representation can be characterized, or can be characterized by a half integer. Okay, a half integer, let's say j. Okay, let's say j. That's what we learned from quantum mechanics. Okay. If we want to represent the SU2, we can classify the different representations by a half integer j. By half integer j. And the dimension of the space acted by the representation is 2j plus 1. Okay? Well, you can easily find from the group theory book, or you go back to quantum mechanics. This is the fruit for the job about the representation of SU2. Okay? So this is the second. First one, I should remind you, this is nothing but the Pauli matrix of relation. Second, all these representations are already known, okay? For SU2. Just classified by a half integer j, and what this sentence means what? This sentence means, as mentioned earlier, you can see this square matrix is a representation. You can also see the vector is a representation. Okay. Here, I mean, for the representation, I mean the square matrix representation. Okay. The point is, the space or the vector space, usually used for the vector space, the dimension of the space, which acted by this square matrix, right? There's also a dimension. So if you want to count in that dimension, you get 2j plus 1. Okay. Let's check what does this mean. So if I want to specify to a particular representation which j equals to half, for example, okay, this is called a half spin representation, okay. So when j equals to half, then 2j plus 1 equals to 2, right? This just means for spin half representation, there are two components, okay. There are two components for the spinner, and your sigma or Pauli matrix can act them. Okay. Is that clear? So there are two different space. One space is so in the for Lorentz transformation, this space essentially means the four Lorentz vector, okay, space. So dimension of this space we call it 4, okay, not 4, okay, because there are 4 components for the vector, okay. The dimension of that space is 4. But yeah, now we're talking about the SU2 first. To talk for this, the purpose of doing this is to further clarify the entire Lorentz group. Therefore, number 3, because of the above classification, the irreducible representation of the Lorentz group and are characterized by 2 half integers, right? Right? Because there are 2 SU2, okay? Because there are 2 SU2. Each SU2 is classified by a half integer. Now you have 2 SU2, just put them together, okay? Then you should have 2 half integers, okay? Sometimes we just denote it as m or m comma n, okay? We put these 2 half integers together to label my representation, some particular representation. We use a comma here. Okay? So m comma n. Both m and n half integers. We use this symbol to specify one representation for my Lorentz group. Is that clear? Okay? The logic is very clear, right? What I'm just trying to convince you is Lorentz group can be decomposed into 2 SU2. Now, provided you already know all the stuff about the representation of SU2. Now, I'm saying a little bit more claim is that the Lorentz group representation is this m comma n. Okay, that's it. And how many degrees? How many of the dimensions? So for each m, according to this counting 2j plus 1, we should have 2m plus 1, right? Right? Now for another n, you should have 2m plus 1, right? Right? As said, in the algebraic level, they are just a sum together. In the group level, you have to product, okay, take product. So the dimension, the representation of the group, if you want to count the dimension, now the dimension becomes the space which this representation acts on. The dimension of that space becomes 2m plus 1 times 2m plus 1, okay? So this is the total counting. So it seems this classification is something new, right? We didn't really learn or discuss this before. The immediate question is how to connect with what we already know before, okay? How to connect this, how to make the consistency between the classification here and what we already know before. This is the next question. Can you see something? Because we already know many examples before. Okay. Now remember that this claim is a little strong. But it says all the representations can be classified this way. Okay. Okay. All the representations can be classified this way. But we do know some representations before, no? Right? We know there is a tensor representation. Okay? There's a Lorentz tensor. There's a Lorentz vector. Okay? All are these the irreducible representations. They are not unitary, but irreducible representations. Okay? Also know scanners. Okay? So how to fit these two? These things, these are two different points of view. Then how to fit them together? How to make the consistency? That's the question. So the relation goes as follows. The previous Lorentz tensor representation, for example, we learned many tensors, right? Maybe an n-ring tensor, maybe an n-ring tensor. This n is not necessarily to that n, so it's different n. Previously, we do know some Lorentz tensors, a general Lorentz tensor, n-ring tensor can be written this way, okay? For example, T mu nu, okay? A mu, okay? A mu is rank 1, T mu nu is rank 2, okay? And this is the rank n. For that rank n tensor, if you want to categorize into this classification, which classification here? This belongs to which classification here? Then the answer is this is the n over 2 representation. Right. It belongs to the tensor before. Okay. Belongs to this one. Okay. It belongs to this one. Okay. So there is a relation, as I said, because the sum or the decomposition theorem 2SU2, then you can build up the relation in a very concrete way. I'm not going to do it here. It just tells you there is indeed a relation. Okay. For example, when you talk about A mu, you can say A mu belongs to the representation half and half. Okay. You see? Okay. Previously, we think that this is a Lorentz vector sometimes. Okay. Before we talk about this half integer 2SU2 classification, we saw this is a Lorentz vector, okay? And we can also promote the Lorentz vector field, of course. Okay. But for simplicity, you can think this is the Lorentz vector. The point is Lorentz vector belongs to half representation here. Okay. Okay. This is not the, sometimes this kind of representation can include something more, but we don't want to specify this relation in a very concrete way. We just tell you it belongs to this, okay? Meaning that some other object also belongs to this, okay? This representation is a little bit larger than only included this one, but this indeed belongs to this one. This also belongs. This is a claim. Then this build up this relation between the two understanding. Okay. So what else? So another important remark is, of course, emphasized many times. This classification is really different from Wegener's classification. Okay, don't confuse. Don't confuse. This representation, or this classification, is geometric. While Wegener's classification is more physical. Because it defines the particles, okay? As you can check, okay? As you can check. Why? See, from here, as said, A mu in here belongs to this kind of representation. So let's count the degrees of freedom. Okay. Since there are two halves, let's plug in with this m and n. So I will get 2m plus 1 is 2, okay? 2m plus 1 is also 2. So 2 by 2, I get 4. So from this geometric classification, you might naively say, okay, if you give me a vector, I will get 4 degrees of freedom, okay? This is really a naive counting, as you can see, right? This is almost a naive counting. The naive counting is consistent with because mu can run over 0, 1, 2, 3. You can naively say there are 4 degrees of freedom, okay? But Wigner's theorem tells you, no, it's not true. More careful, okay? You have to impose unitarity, okay? Then you have to do more work to really find the physical degrees of freedom. Okay? The physical degrees of freedom is not 4. It's not 4. It depends on the mass. If it's massive for mu, you get 3. Okay. If it's massless, you actually only get 2. Okay. It's a Wigner's result. But this classification doesn't touch that yet. Okay. It's only counting the so-called geometric. Okay. Geometric way. Okay. Geometric means it's not physically. It does nothing to do with the physical realized state. It's just a geometric structure. Just some tensor structure. Okay. So this is the important difference between this classification and the Wigner's classification. Okay, so after all this preparation, now we are ready to talk spinors. Okay, so spinors can appear from here. Appear from here. So we can ask this further question. So to get spinor, the question we want to ask is, all this previous representation belongs to this kind of, okay? Okay, it looks very symmetrical. It's a half, it's n over 2, n over 2. But what if I want to ask, since nobody forbid me to make this m and n are different, okay? So the question I want to ask, what about the representation for these two kinds of 0 part, okay? And that one or m or n equals to 0, another to half. Okay, this is a good classification. You only require m and a half integer, so this is the simplest choice with a left and a right difference. Okay, so what about this representation for this or this? Okay, so this is the question. Now the answer is almost there, right? It's almost here, right? It's almost here. Because we already know m or n specify each SU2, okay? There are 2 SU2, right? Now, one of them is 0. 0 means it's trivial, okay? What do I mean by 0? 0 means it's a trivial representation. Do you know what is a trivial representation? Do you know what is trivial representation? All the element, just only element is identity, okay? You can easily justify. Identity can represent anything, okay? Anything, right? But it's just trivial, okay? It's just trivial. So why is it trivial? I mean, one of the SU2 is trivial, belongs to the trivial representation. Another is half, okay? Another is half. So another is half. It essentially means this J equals to half. You see? Because I already classified the SU2 by J here. So one of the J is half, and 2J plus 1 is 2. Okay. they almost count to you. This counting already tells you that vector space, that space actually by this representation. This should be two-dimensional. Okay, it should be the two-dimensional, and because of that, the transformation matrix act on the two-dimensional space should be 2 by 2. Okay, you see, should be 2 by 2. And very fortunately, we already have an answer here. This is a 2 by 2 choice, you see. So for this particular question, I already know sigma, I can use the Pauli matrix, okay, to represent all these generators. Okay, is that clear? Because just from the counting, you see, just from the counting, you should have a 2 by 2 matrix to represent these generators. Now I already have a choice, which is the Pauli matrix. Okay, so because of this, I can, because of there's a choice. Because of we already know there is a Pauli matrix commutation relation sigma I sigma j divided by 2 commute equals to I ijk sigma k over 2. Okay, this is the Pauli matrix commutation relation. Because of this, I can just set the generators to the Pauli matrix. Okay. One can set. One can set for the half zero representation. One can set j I minus. Okay. Let's make a choice to say left corresponding to minus. Okay. Right corresponding to plus. Okay. So for this particular representation, I set j minus equals to half sigma I, and j plus is trivial. Okay. Okay. You can easily just check yourself. Trivial representation is also equivalent to say I set all the generators equals to 0. Okay. You see, if you set all the generators equal to 0, meaning your group element, which is exponential generators, will become all 1, right? This is indeed this is the trivial representation, right? So I can make this setting to realize this representation. Okay. So for the other one, which is the 0 half, I can make another setting, which is the ji minus equals 0, and the ji plus equals to sigma I. Okay, is that clear? And we also know there is a, if you go back to the original j vector, p vector, okay, they can express in terms of j plus and j minus. And this kind of choice also tells you if you want to just keep up. What about the original? What about the original j vector and k vector? In this case, the original j vector is also a half sigma matrix. It's a I sigma. And in this case, the j will equal to half. Equals to half. So we know sigma matrix. Do you know sigma is the Pauli matrix? Okay, this is the Pauli matrix. So Pauli matrix is a Hermitian. Do you know that? If you take the Hermitian conjugate, you get back. Okay. So Pauli matrices are Hermitian. So this I is very important. Okay, this I will be very important. Right? You see, j equals to sigma. So if sigma is a Hermitian, meaning that the group element to represent the rotation, 3D rotation, these are the unitary, okay? If you put the Hermitian operator onto the exponential, you get a unitary operator. Clear? Right?
Yes.
Hermitian means real, okay? You might say, I don't know what you mean by Hermitian. Hermitian is real. Okay? Do you know the number? Do you know real number? Okay, you know reality, right? But if you promote this reality to the operator, that's nothing but Hermitian. Okay. Okay. So that's what we mean by Hermitian. So you can easily imagine that if you have some real number put in here, okay, put in here, okay, then this is unitary, okay, the same thing. Now, if you have a generator which is Hermitian, meaning that the transformation matrix is unitary. So which means for the 3D rotation is okay, but for K is not okay. Okay, why? Because it's I. Okay.
Yeah.
So if Pauli matrices are Hermitian, then I times the Pauli matrix is not Hermitian. It's what? It's so-called anti-Hermitian. Okay, it's so-called anti-Hermitian. So if you take an exponential of this kind of K, then you'll get the anti-unitary. Okay, it's not unitary anymore. It's anti-unitary. This is essentially we see that it's not easy to find a unitary representation of the Lorentz group. You can't find any finite dimension representation. Okay. If you insist unitarity, it has to be infinite dimension. Okay, we mentioned this before in the Weyler's theorem. Okay. Yeah, this is the I is important. You can already see from here. Okay, in terms of the Pauli matrix. So what? So we just make this more concrete for these two particular representations. So what? So now we can introduce the concept of the spinors. What is a spinor? Spinor is nothing but the element of the space which acts by this 2x2 matrix. That's the spinors. So the element of the space acted by so-called spin half representations, or let's say half zero or zero half representations are called spinors. Okay. Okay, they are called spinors. They're called spinors. Now you might complain, what do you do? I mean, you spend more than 1 hour, almost. Yeah, you spend more than 1 hour to somehow to teach something maybe I already know. Because this is nothing but saying that if you have Pauli matrix, okay? If you want to Pauli matrix, you want to use Pauli matrix to represent the Lorentz group. Then the object which acted by Pauli matrix is the spinors, right? This is the conclusion, okay? So why I start little a lot of trouble to write here, essentially because I want to emphasize spinors, we want to use it to describe particles. We want to start from Lorentz group, okay? Instead of just Pauli matrix, like what you learned from quantum mechanics. Spinors belong to representation of the Lorentz group, okay? Because it describes our real world. Everything should fit in with Lorentz group, okay? We should start from the Lorentz group to find the particular representation, okay? Priorly, we don't know the answer, okay? But after this long discussion, step by step, we know, okay, eventually it appears. Why? Because from group theory, Lorentz group decomposes into 2SU2, okay? Then this kind of representation can also represent the Lorentz group, okay? It's just one side is trivial, another is half. That's it. It's a perfectly good representation. Then those objects acted by this particular representation we call those units. Then from the counting, you can also know here. From the counting, you can also know this Spinors has two components. Okay, two components, right? You have two degrees of freedom. A plus minus 2. Right? Because the space, the dimension of the space is 2. And more than that, okay? So, for example, we call this 0-half Spinors. We give it a name. We call this is the right-handed wire spinner. Okay. Or sometimes we use the psi r to denote this object. And we actually already know the Lorentz transformation. Okay. If you didn't miss any step, then immediately now you realize, okay, if I call this object now Spinors, I already know the Lorentz transformation of this object. Okay? Why? Because we know all the chain of the relations among these different generators, right? We also know the Lorentz transformation can be expressed as exponential generators. Is that clear? Now we eventually realize, we make it very concrete how to realize this generated by the Pauli matrix. So you just plug in, okay? Plug in this Pauli matrix into this exponential form, then we get this Lorentz transformation about this spinor. For example, for the right-handed wire spinors, we get this Lorentz transformations expressed in this form. It's not surprising. These are the sigma. You see, sigma is a 2x2 matrix, and the theta, beta are parameters. Okay, so these are just the Pauli matrix. Okay? This is the exponential Pauli matrix. This is the Lorentz transformation. And then for the left, we call this the left. Okay, this is intuitive, right? Right means the right-hand side is non-trivial. Okay, this is trivial, so we call it the right. Okay, the left means the left is non-trivial. We call this the left-handed wire spinors. But just the name. Which one is left, which one is right is the relative choice. And for the left, you can also work it out. Easy exercise, the Lorentz transformations. Okay. For the left wire spinors, the difference is here is plus, here is minus. Okay. Now, start from here, you can also say, justify what I said before. This is not a complete, this is not a unitary, okay? Right? This is the Lorentz transformation atom spinors. Now you can check, this is not a unitary. Essentially because there's no I here, okay? Right? This is real, this is Hermitian, and this is real, okay? And there's no I here, and then you have an exponential. Then it's not unitary. Okay, it's not unitary. So this representation is not unitary, but it's a good representation. It's a good representation. It's just not unitary. So this distinguishes from the Wegener's classification. It's just mathematical classification, it's not physical. Yeah, so the natural question next is, now up to here, we almost learned how to introduce the concept of spinors, right? But this is just the spinor, but not yet the field. Okay. So the real interesting question we want to go further is we really want to find the unitary one. Okay. Okay. From the experience, in order to find the unitary representation, you have to quantize. You have to first promote it to a field and then quantize it. Okay. Only by doing that, you can find this infinite dimensional unitary representations. Okay. Is that clear? That's what we learned before, right? Only in this case, you go to, after quantized, you go to the momentum space, right? So you construct your physical state as a single particle state, okay? That state is it has the infinite dimensional parameter momentum, because momentum is continuous parameter. You have infinite many choice. So this is the infinite dimensional representation, okay? This is the next step. So before doing that, we have to learn how to construct the Lagrange. We didn't touch the Lagrange yet. We have to first talk about how to construct the Lagrange for the spinors. Once you have a good Lagrange, and then you quantize it, then you eventually find what you want. Okay, it's a spinor particle state. Okay, which is the unitary irreducible representations of the Lorentz group. Okay. Let's have a break and we will continue. 所以我在最后的话，他们要收这个分对数字啊，
就是没会过嘛，就随便选，反正就两个这个，我肯定没会过，我肯定没会过，
所以就是这个数字资料，
但我
这个直接性，
一个是这，对呀，那个应该可以算表示，就我们之前算过那个，算过来是的，现在是算过一个表示取一个换旧词，所以说今天我就说这个字源，它是根本就没有算这个表示，甚至这个也不啊就要这个这个项目。那个基
它是对应是二分之一二分之一，但是能解一下这句话。
就是这是一些上面的要求，我之前说的，无意的不太一样，我们就对加入了。
一般我们看
这么一好像就别人的话，他真的真的就别人写着方言说，那个只是那个
我应该没好，这个没
再说我们可以开始变异的对，这种分子是几乎提出一些一种的表示，其实这个表示，我不再表示的一些，它的这个表示那个上面形成感的一些，就是包括一些以后的一些名字，比如说那会我们在那个期就once，在那个 S 一表动量的那个情况下，那种换一个就可以。来估计更好是那么做到这个选择。
所以就是这个是我就是我选的这个东西来研究它会有一个尝试，它的表示会有一个。
他现在没有问题，他就如果我选他我们是这样数字，那么所以我就在我就是凭这个思路来的下面对吧？谁会随便选的？
如果是0/2的话，那是相当于就为这个这里是1/2，不对，不对。
另一个角度
2/1可能
我可以认为它是一个周期。同样在一个是正的地方，因为或者有，那就写，就它甚至有一个EXP，我对它的话，你那个 I 相当于高拍的讲了。
OK。
如果所以说如果一个这个情况，
所以就
就可以用400，
但是相当于
就出来太阳有个正轨。对，它是有的。讲的比是变因子，我们知道的两个，我没讲对，那我听一下，对，就不是这个人，他那种变化，对，看这个温球掉，
那海参堡可以加
对，回转也是可以。
我感觉这个应该是在那个。如果有的话，可以。我相关这个位置的话，可以这到这里边，一个是一样的，因为升到顶这里，到最前就出来。
给你类的。我不对。
是分有一个
但是又是
那怎么可以？谁在手上？但是上一回来分血了，是黄血了吧？不是给他打部分。神仙天啊，不用了。他没来直接克走啊，
谁人来肯定全教授都知道的。
没那么早，其实。
他那个是低调。这个没有啥的，没有，就是应该有。球确实。我是不太知道那个没有想。就看。那个，
得让他头像发上。新的认识的意思就是你看，
那就是电子，
但是他不是说那个对说那个
啊，这个是没有外的，电子是个加这个。但是嘛，两个外的多做六个那个单位一样。
就你如果0.2的话，那你就会不对应着一个真实的例子，然后这样也有吗？
我上例子，你求例子，你求标准模型，求例子，知道吧？这个对吧？然后因为
对，他变完之后他就有啊，他们管出来这个，以为是盖的
没有，他应该没有，标准模型应该没有。啊，一个没求例子，没求过标准模型，没求过。
啊，就是因子力学。
我不但学有一个8，就是不是那个对吧？8是这样，对吧？不是有然后黄对吧？这个那个哦，我这属于刘备有营养。是历史。你们发后，我终于把这个清明改为
你都背景照片。 查的不是像谁的更大。
所以说我就没动过。
我好，还有3、4天红傍晚都不给你看。
总说有。
So that's the question we want to ask to compare how to construct good Lagrange for the Spinors. By good, we mean the Lorentz invariant. That's the key property, right? Compared with some others, at this moment, we should focus on Lorentz invariant. So how to construct the Lorentz invariant out of the spinor? That's the question. That's the question. First of all, this kind of spinor is a little abstract, but what you should keep in mind is you should always think that there are two components of this spinor. We mentioned because of the dimension of this space is 2. Okay, dimension of the space is 2. The spinors we often write it in like a column vector. Okay, but it's not. It's actually not a vector. Okay. So when you ask me, it just seems the format the same. How do I distinguish this is a spinor or vector or what? The point is the transformation defines. Okay, whether this is a vector or spinor. Okay. You shouldn't just look into this form. It doesn't make much sense. Okay. If you transform it, okay, you see the transformation property. This transformation property defines whether this object is a vector or a spinor. Okay. Okay. So spinor is also like in this form. When you Lorentz transform it, you will see the transformation is different from the usual Lorentz vector. Okay. So how to construct Lagrange? Okay, how to construct Lagrange in terms of, for example, we introduce the left or right, then you may ask how to construct this Lagrange in terms of this left or right. Okay. A complete field theory Lagrange, of course, will depend on this spinor field. Okay, as a wire spinor field, you have to first promote it to a field, right? Then you write down a field, a theory Lagrange. But even before that, we even don't know what are the Lorentz invariant combinations of these spinors. Maybe you should check that first, right? Okay, following our experience. Previously, we said, okay, when two Lorentz vector, the index is contracted over, it automatically Lorentz invariant, right? The following that experience, we construct our first third Lagrangian, let's say partial mu phi, this upper and lower mu contracted over. We know that kind of object is indeed Lorentz invariant. Okay, so we should first check some transformation properties for this. This Spinors. Okay, for Spinors. So, as said here, let's say, this is we know the Lorentz transformation properties. Okay, for example, this is equation 1, this is 2. 1 is for the right, 2 is for the left. From there, we can do a small parameter expansion. Okay, we can think theta and beta are small, and do the expansion. Then what we get is this under small parameter expansion, the right-handed wire spinor will transform to some spinor acted by some sigma matrix together with a small parameter. Okay, this is just to do a small theta, both theta and beta. Okay, expansion. You get this one. Okay, you see, that's the exponential ix roughly. This is the 1 plus x. Okay. So from here, we can work out the infinitesimal transformations of the spinor. Okay, infinitesimal transformation of the spinor. This is the half I sig j plus beta j sigma j back from c psi, right? Okay. So why will we care this? Because this is the infinitesimal transformation of the spinors. Take use of this one, we can justify which kind of combination of Lorentz invariant. Okay. And from our experience, instead of think about a finite transformation, maybe a little bit complicated. Infinitesimal transformation is much simpler. So use this infinitesimal transformation, we can judge which kind of combination of Lorentz invariant. Okay. So for the left, this is the half I theta j minus beta j sigma j. Okay. For example, let's check. There's no really clever way. Just check one by one, mostly. Okay. Just check. Just do experiment. You just check or test. For example, you might think about, okay, since this is your spinor, we might want to consider something like this. Okay, this kind of combination, right? Right? It's a dagger. So what do you mean by this dagger? You transpose, okay? You transpose that object, and then what? Yeah, you do the conjugate, okay? Then you get this one. Then you might see this kind of combination. It seems you get some function, okay, or some number, okay. Depends on your asking field or the vector itself. So you might think, maybe you can try this one and to check the Lorentz transformation. Okay. But very unfortunately, when you check this one, I don't need to check the finite transformation to judge which one is invariant. Okay. Infinitesimal is enough. So let's check infinitesimal of these combinations. So we can work with this out. So after a few equations, it's not difficult actually. Then you get this is beta I psi plus sigma I psi r. Okay. So it's not invariant. You see, because this is not zero, right? This is not zero. because this delta is infinitesimal Lorentz transformation. I act on this object, I still get something not zero, okay? Which means this combination is not good enough. So what? You might somehow try some others, okay? You might want to try something like this, okay? Why I want to consider something like this? Because this dagger is a transposed, okay? And this is a column, so this is a row, okay? And in the middle, you can insert some matrix, okay? Still, you get a good combination, right? That's the possibility. So you can maybe test this one. Then after a few seconds calculation, you get this one with beta I psi plus the dagger, cosine R dagger cosine R minus theta j epsilon I j k psi R dagger sigma k psi R. Okay? If you try this, then you get this one. Like, yeah. So you observed something very interesting, right? What is that?
Vector.
Yeah. So this transformation is nothing but, I erase it for this transformation is nothing but the X transformation, the Lorentz vector transformation in terms of component equations. Okay, what I wrote to you before in the very beginning of today's lecture. Is that clear? You remember that? In the very beginning, we wrote something like delta x0. Remember that? Equals to something times xi. Okay, remember that? Actually, it's the same thing. Okay, parameter is the same. And delta xi equals to blah blah this one in terms of the x0 and also xi. Remember that? So this means that this is roughly roughly you can think about this is the x0 before and this is the xi. Okay. Okay. And x0 and xi are the component of Lorentz vector. Okay. Remember that? The same transformation. Go back to your note. You realize that, okay, combined with these two, there's a very interesting observation, which is instead of consider this single term, we should view this term or this term as a component of a larger Lorentz vector. Okay, that's the lesson. That's the lesson. So if you like that, then meaning seems very straightforward. So the observation is here is this entire thing psi r dagger psi r comma psi r dagger sigma psi psi r. This is a single component, and this index run over from 1 to 3. The 3 components here form together. This object is a Lorentz vector. Therefore, something like this in the Lorentz environment. Okay, something like this is Lorentz environment. You see, because I contract this kind of vector with a partial norm. Okay, okay. you can check this stuff is indeed the Lorentz invariant. So this kind of terms gives the construction of the kinetic term for the spinors. And of course, there are some other choice which you can check it relatively easily. For example, some terms like M psi L dagger psi R closely combined, okay? Plus psi R dagger psi L. Yeah, some terms like this is also the Lorentz invariant. Okay. The point is, you combine the right and the right itself is not the Lorentz invariant, okay? But you can check it relatively very easily. We combine left and right, okay? I can also do this choice. If we combine left and right, or right and left, these are the Lorentz invariants. These are the separate Lorentz invariants, okay? So we found this kind of structure, something like this, and also this is Lorentz invariant. Okay? So we can try to write down the complete Lagrangian, something like this. So for the spinors, it means what? It means if you want to view this kind of mass term, this looks some mass term, okay? If you want to view this as a mass term, it seems that in order to turn on mass, okay? In order to turn on mass for the spinors, you cannot do separately for left or right. You have to mix, okay? You have to mix, okay? You have to mix. This is the physical reason why we need 4-component spinor to describe our electron, okay? Because our electron is massive. Be clear? So if the electron in our real world is not massive, meaning this m equals 0, then we may only need the left or right to describe the electron. Unfortunately, it's not. So because our electron is massive, so it has to involve both left and right. Okay. So each one has 2 components. Therefore, they put it together. We have 4 components. Okay. That's why later we will see we have to use Dirac spinor. Okay, which has 4 components to describe the electron in our real world. So you see already from here, everything come out of the representation of the Lorentz group. Okay. By Lorentz invariance, you already see for massive spinors, you have to involve both left and right. Only a single left or right doesn't work. Okay, it's not enough. Okay. Yeah. So the complete Lagrangian will be something like this. Okay. I psi r dagger sigma mu partial mu psi r plus I. Because this is I only discussed in detail the right-hand side, right-handed wire spinors, but the same story for the left. Okay. So dagger sigma r mu partial mu psi left minus m psi r dagger psi left plus psi right. Okay, this will be the complete Lagrangian. And of course, you asked me about the location. For example, this is sigma. I define sigma mu 1 sigma hat, and the sigma bar mu as 1 minus sigma hat. Of course, we know what is sigma hat, right? Sigma hat is the three poly matrix. Okay. This is my notation. Should I use the sigma bar, sigma here? Okay. Now you still ask me why you put the Finding factor I here. There's an I appear here. You can easily check yourself. Without this I, this entire combination is not a Hermitian. We want every term in the Lagrangian to be Hermitian, meaning real. Okay, again, it's the same thing. Okay, like a real number. Okay, we want it to be Hermitian. This I is for that purpose. Now we're almost there. Everyone, we already got this Lagrangian. Then the next thing is we can repackage a little bit, as that already mentioned. We can use the forced binary language. Okay, we can rewrite this. We can rewrite this. Rewrite the Lagrangian in terms of a psi, which is defined as the psi L and psi R. Okay? And each one has two components. Okay? You see, now I put them together, we have 4 components. Right? We have 4 components. This is just a rewriting. Now, we can also rewrite the psi bar in terms of psi R dagger, psi L. Okay. All this you can use it in the definition, so it's not a big deal. Okay. I just define this way to make this Lagrangian more easier. Okay, more easier. So if you define this, it this way, then your Lagrangian becomes very, very simple. You can check your Lagrangian. I further define something like this. I define a 4x4 matrix. Okay, 4x4 matrix in this way. As I said, each sigma is a Pauli matrix. Okay, so each sigma is 2x2. I put these 2 sigma in this way, so it's a 4x4 matrix. This is called a gamma matrix. We call it a gamma matrix. So after all this preparation, you can justify yourself. The same Lagrangian here is stop. The star Lagrangian now becomes easy form. Yeah, it's very easy. That's this one. It looks like a single term or 2 terms. It's very easy. Very easy. So this is what? You know what this is? This is Dirac theory. It's one of the most famous equations in history. Okay, physics. Okay, which is Dirac discovered. Okay, if this is the first time you see this form, we need a little bit more understanding how to understand this kind of thing. It looks a little strange compared with what we know before, right? Previously, we only know equation of motion or Lagrange for scalars or Maxwell, these types. We never see something like this, okay? How can I understand this? Why does this kind of thing make sense, okay? The first question you could raise is something like this. Of course, I escaped some more details, but I just from Lorentz invariance tells you this kind of combination is a good kinetic term. Then you immediately ask why, okay? All the previous examples, including the free scalar and the Maxwell, we see the kinetic term has two derivatives. But this time only a single derivative. You see it? Yeah. Then you should ask yourself, why does this make sense? Okay. Does anybody know the answer? Why this single derivative makes sense here? The magic is included again in this sigma matrix. Okay, you can check this out. Okay. Even though it looks like a single derivative, okay, here, but since each spinor has two components, okay, so this is actually a matrix combination, okay. This derivative is actually a matrix, a derivative, okay, because there's a sigma matrix here. So this kind of structure, essentially makes such kind of combination is equivalently to say like a second or twice derivative act on a single component. Okay, this becomes more clear in the equation of motion level. Maybe I should first write down the equation of motion. It's a little hard to explain in the level of Lagrange. But okay, so the equation of motion can be derived very straightforwardly. Because in this language, we always view this psi bar and psi are independent variables, okay? So from this Lagrange, we should derive equation of motion by do the variation principle, right? By do the variation principle. Now, if these are the independent, I can do the variation respect to the psi bar, I will get the equation of motion for the psi, okay? Then that equation of motion is very straightforward. It's nothing but this equals to 0, okay? So it's I gamma mu partial mu minus m and psi equals to 0. Okay, equals to 0. This is called the Dirac equation. Okay, of course you can also write the Dirac equation in terms of two spinors, right? This is just an elegant form in terms of four component spinors. You can also do for the psi L. You can also do it for the psi L and psi R. Okay, is that clear? No problem. Okay, no problem. The only thing is for m is not equal to 0. This two equation motion mixed a little bit. Okay, meaning that left associated with right, okay, because of m non-zero, and the right associated with left because of m non-zero. Okay, now. At this level, still, you can ask why there's a single derivative. It's the same question you asked before, right? Why there's only a single derivative here is essentially equivalent to ask why in equation of motion this is a single derivative. Okay, same question. Okay, why? The point is as follows. This object has the component. Okay. There is a non-trivial matrix in front, okay? If you work this equation in great details, you realize that you're handling some differential equation, evolve a matrix, okay? Then you can decouple. You can decouple because differential equation in terms of matrix is like many equations, okay? Quite often, these equations are not decoupled; they are mixed. Okay, mixed means this component evolves the other component, in this equation of motion. then you have to decouple it, okay? When you decouple it, you indeed get the very, very familiar Klein-Gordon equation, okay? Is that clear? So it's not strange at all. It's just that you somehow you express the second order differential equation in terms of the first order differential equation, but the payment is the object. The object or the variable becomes a matrix or a vector. That's it. Is that clear? First order differential equation involves a different component, can be equivalent to a second order equation, but for a single component. They're the same thing. You can easily check this. Okay. So this explains the magic why this equation of motion looks first order. Well, what I'm telling you now, when you decouple it, indeed it becomes second order. Okay, it's not a big deal. Okay, is that clear? You can easily imagine, right? When you have a matrix equation, you have two lines equations. They mix. Okay, each line of this group of equations is the first order. But when you decouple it, it becomes second order. Right? This is quite not a big deal. The same thing here. Okay. Good. So we call this is also has a famous name. We call this is a gamma matrix. These are the gamma matrices. And I already introduced them called here, but I didn't write it in this form. You can write it more explicit way, and the mu can run over from 0, 1, 2, 3, which means there are 4 gamma matrices. Okay, 4 gamma matrices. For each mu, the gamma is a 4x4 matrix. Okay, that's another concern. You have to pay attention to this equation. Even though this equation looks very, very simple, but the content is not simple. Okay. There are many components in this equation. How to understand this equation? This equation, you see, we have a mu index here, right? Of course, this mu index contracts, okay? But the point is, for each mu, contract means there's a sum, okay? Sum, there's a some different terms. But for each mu, the point is, the gamma is a 4x4 matrix, okay? And act on this 4-component object, right? Everything like this is hidden in this equation, okay? This equation. So it's not a simple equation, even though the form looks simple. Okay? It's not a simple equation. So another comment is, the explicit form of gamma matrix is not unique. Okay. This is called the gamma matrix, but just like before, just remind yourself, where does this come from? Gamma matrix come from sigma matrix, right? Yeah. Where does sigma matrix come from? Sigma matrix come from as the generator, okay? Or it's the generator of Lorentz transformation at some point. You see it? But we mentioned already in the very beginning, all these explicit matrix form, they are not unique, okay? There's some intrinsic properties for this kind of object. Same thing here for gamma matrix, okay? So you can view the gamma matrix as some combination of Lorentz generators acting on the spinors, okay? And there's some intrinsic properties for this kind of object, okay? This is more fundamental than the explicit form. But the point is the representation. The point is the representation of the gamma matrix is not unique. It's not unique. It's not unique means there are some other forms for the gamma matrix, but it's the same gamma matrix. Okay. So they are not unique. But some algebraic relation, once again, some algebraic relation is more fundamental. In this case, you can check. There's something called the anti-commutation relations. For 2 given gamma matrix, you must get 2 G mu nu. So from this exclusive form, you can derive this one. But like what we learned in the Lorentz algebra, okay, language. You get this kind of relation. But once you get this kind of relation, you should view this kind of relation are more fundamental, okay, than some exclusive form of the gamma matrix, meaning that there could be some other exclusive form to represent the gamma matrix. All of them should satisfy such kind of relations, okay? So that's why we use such kind of relation to define gamma matrix. So this is called the Dirac algebra. Dirac algebra is one of the three-fold algebra. But we do have a particular representation here. Remember that where we start from? We start from the wire spinors. You remember, right? We start from left or right, and we combine them together. We eventually have the four component, the Dirac spinor. Okay, so we right from the start from the wire spinors. That's why this kind of representation, for this particular form, we call the wire representation. Wire representation. There is also some other representation, the Majorana representations. Yeah, there's some other representations called the Majorana. Of the gamma matrix, okay? Should I write this? Yeah, let me try to write in 10 minutes. Let me write this. So in Majorana representations, this gamma matrix will equals to some 0, 0, sigma 2, sigma 2, and gamma 1 equals to I sigma 3, I sigma 3, and gamma 2 equals 3, 0, 0, gamma 2 minus 2, gamma 3 equals to minus I sigma 1. Minus I sigma 1. Okay. Then you ask, what is why this is interesting to show this another particular representation, so for the Majorana representation. Yeah, we don't have time to go to the details to introduce the Majorana fermion this time, but let me just mention why this is very interesting. Okay. So as you can imagine, now we're working on this wire representation. Essentially means the Dirac spinor can be decomposed into the can be decomposed in this way, right? You see? Right? This is my Dirac spinor. Can be decomposed into left and right. Okay. But you can imagine not necessarily to be such case, okay? If you switch to some other base or other representations, okay? For example, I can change my gamma matrix, okay? Go to some other not wire representation. Then this may mix, okay? You may not get such simple decomposition. This part, upper is left and right, lower is right. It's not, in general, it's not. In general, it's not. That's what we mean by go to some other representations. Okay. Another comment is in this Weyl representation so far, we write if you write this spinor explicitly in terms of two components. Okay. In general, we think that these two components are complex valued. Okay, a complex value. It's not necessarily to be real. Okay? It's a complex value. Why? Because this should transform under Lorentz transformation. You see, under Lorentz transformation. But the point is, the Lorentz transformation itself. The Lorentz transformation itself is a matrix which is complex valued. You can check it. Okay. Okay. So I have an object. Even though you start from some object with real component, real means real valued. Okay. Then, since the transformation matrix is in general complex valued, then after a single transformation, you can easily become a complex valued. Is that clear? There's no way to preserve the reality of the spinor. Okay. There's no way. Essentially, the Majorana gamma matrix is prepared for that purpose. So next time, we will go into the details to see why in this particular gamma matrix, we can insist the reality of the spinors. Okay? Okay, is that clear? The point is in wire basis is not possible. Okay, we already explained why. Because in wire basis, you can see the Lorentz transformation, this kind of things explicitly, they are complex valued. Okay, but now I change my base completely different base, then I can justify the under this new base in this new base, even though under Lorentz transformations, the reality of the spinor can be preserved. Okay, that's why we call this is Majorana spinors. Maybe you learned from some popular science article about the story of Majorana spinors. No? Yes? Yes. Do you know what's the definition of Majorana particle, Majorana spinors? The easiest definition, what is that? Easiest definition is the antiparticle is itself, okay? For Majorana particle, the antiparticle and the particle are the same. That's why we're now talking about the reality. Look at. So roughly speaking, if you take a complex conjugate, we usually think from particle go to antiparticle. Is that clear? Okay? But if the object specifies the conjugate equals to himself, okay? Which means the antiparticle is the particle itself, okay? Right? This is the definition of the Majorana particle, roughly, okay? But we will see the very precise way to derive or justify this maybe next time. And just a few words. The Majorana is a really magic physicist. You know his story? Majorana is a very interesting physicist. Yeah, he invented this Majorana spinors at a very early age, right? And then at some point he just disappeared. Nobody knows where he is. Okay. He died or he's still alive. We don't know. Yeah, he's a genius. Yeah, he's the first guy who realized in the language of spinors, the antiparticle and the particle can be the same. Yeah, can be the same. But from experiment today, we still didn't observe from any experiment the Majorana spinors or Majorana particle. Okay. As you can sometimes see from the scientific news, some condensed matter people claim they found the Majorana particles, blah, blah, blah. But they're not the really fundamental particles for sure. Okay. Somebody guess maybe a neutrino maybe perhaps is a candidate, or Majorana particle is a candidate of a neutrino. Okay, that describe neutrino, but it's not confirmed yet. Okay. So these are the discussion of the Spinors. So do you have any question for this part about either Dirac equation or the Weyl Spinor representations of the Lorentz group? Any question?
I have a question. 就如果我们想讨论更高自旋，是不是只需要把那个辅正换一下就行了？把辅正，就比如说我们想讨论自旋唯一的例子，那是不是只需要把那个泡力矩阵换成一个三维的泡力矩阵，然后其他的东西都完全一样
？No, spin one is not for three. 三维啊，怎么得到三维？
就我的意思是，就比如说，我们想讨论一个自旋更高的一个例子，是不是只需要把那个矩阵换一下，就其他的完全
？Yes，就是根据那个 counting 是2J 加1 ，OK。那么你现在差不多了，现在有两个 J，
全为一的
，1J two。Maybe you can count it.
差不多
OK，
2平。
So half 就是4 ，number 是4。那么 principle 你可以 embed 到一个4维。类似在，4，
剩下的东西就
对。
我可不可以让3/2、1/2这样子？
是，
这样出来是什么东西？
啊，就 higher spin， control 到 higher spin particle， 3/3就是多少？4416。Yeah. So indeed, in the spin theory or supergravity, for example, quite often we use the 16 component or 32 component spinors. It's not a big deal. 好，没问题，可以下课了。没问题。
我也不知道我讲。
然后谢老师。
做的时候讲介绍。
妈，关于那个两个，我下午再说3点去的，
没有，我还没看啊，我还没看，我在大他明天还有可以啊，有下午啊，明天下午2点半，
先把这个写，对，
看到几点憋住？
看一下这个网上，下一个。它是一个4维的不同的
一个我有自己啊，我有是，我有自己，
我是对的，那我明天对着看。
OK。
我也是男的，
我也睡觉了，我的健身的讲完。对，这个聊特项目。那我
不是不知道，
这个线它会用的就一个坏，
他应该是他写出来是个，
这儿不完全是个旋转的，
他写出来是个，
是 J minus J plus， 真正之前物理的
这
旋转。
个横的乘以4×4再乘一个竖的，
对，
写出来是同样的，
像这样。这个意思。你看这个 J plus J minus 是，就 formally 是个旋转，不是真正物理旋转，是双方再组合了一下，组合了，按 formally。 这个 often
占导数，罗汉导数是按照另外一边这个四方面，
这个
就是每个非常非我说的就是乘成一个数的话，就第一个就是左边出来就是一个1乘4的
因为 AMU 我们知道
黑板它现在是用新数大黑板，
为当
合在一起就是一个
数 vector 或者
3化的一个列向量的一个方程，
那么这个2分之一加
应该是一样的。
所以我就可以相信，
但这个方程对，这个方法是全的，两个
就是可以写
两个直合的
两个 x
两个直合的algebraic level，用两个直合的群拼在一起，然后你可以得到一个分数。
求完之后这个
体积吧，就全量我就体积，这个你的
这应该是个乘一个列向量，数字向量。
代数 level 是直合的，不是体积的。Anyway， 你应该是就是他说把两个2分之一的 expression 拼到一块儿，
那就一样的嘛。
对，实际上对，that's right，实际上你的
对分量的，
然后0那个1的过程，
这个要求完导之后，运动方程仍然是一个矩阵方程，就有这个这个式子的这个矩阵方程，相当于
AMU是有4个分量的，所以你随便往里框进一下也是4个呀。
对，然后要
2分之一乘以2乘以1，
4个全量是
乘以另外一个。